Assalamualaikum and good evening to Doctor and my fellow friends. So today we will present about our project, which is suspension system. So without further ado, let us begin. So as we know that vehicles consist of many systems such as vibration system, engine system, and others. And all the system have their own functions that related to each other, such as vibration system and suspension system. They have relation to each other so that they can function very well. And there have been large research achievement in the automobile suspension system, such as the optimization control theory, the PID theory, the theory of variable structure control, and the skyhook damping theory, which have been applied generally to the vibration control system. And we know that nowadays engineers have used the software system to in order to get the accurate value rather than running the experiment in lab. And the software that they use is MATLAB because MATLAB is MATLAB have their own function that can calculate the accurate value. Okay, for the project background, for our project, we try to use the bigger object to determine the resonant frequency of the acceleration of the bus. As we know that the bigger object, the bigger the oscillation when the bus bump into the something on the road. So for our program, for our coding, we try to reduce the frequency of the oscillation of the bus. And our programs allows the engineer to calculate the accurate value of oscillation of the bus to make sure that it can reduce the oscillation and bump in the bus. So it will be easier for the future engineer to calculate the value later on. So thank you.
For the MATLAB program, first we are going to derive the basic equation of the system and find the transfer function and examine the open loop unit system. So firstly, we are going to assume that all of the initial conditions are zero, so that this equation represents the situation where the vehicle wheel goes up a bump. The dynamic equation above can be expressed in the form of transfer functions by taking the Laplace transform. The specific derivation from the above equation to the transfer function G1 and G2 is shown below, where each transfer function has an output of x1 minus x2 and inputs of u and w respectively. So the inputs we are going to use in the system is the value of mass of the bus, M1, the value of suspension mass, M2, the value of suspension spring constant, K1, the spring constant of wheel and tire, K2, the damping coefficient of suspension B1, the damping coefficient of wheel and tire B2. So to gain the transfer function G1 and G2, we are using the equation that we got from the calculation we have done in the project into the MATLAB program. We are going to make the transfer function, which is S, to create a continuous time function of variable S, which can be used in defining the transfer function models. Then we are going to do the 2D plot to see the result of the open loop system. So based on the result, because the open loop system show the result, the amplitude is too high and long for the system. This will make the bus oscillate due to the large overshoot and long settling time. So we will do the closed loop system. Okay, next slide. And now we are going to use the same input for the closed loop system. So this equation is for discrete time transfer model. And then we are going to assume the proportional gain, which is Kp, and integral gain, Ki, and derivative gain, Kd. And then we are going to derive the PID object, which is C, to generate an equivalent continuous time controller. And then we're going to simulate the response of the system by finding the transfer function from the road disturbance W to G1. And uh, and then we should get the result of the feedback. Okay, next slide. And then we are going to plot 2D and 3D graph for the response for the step response uh, to a 0.1 step response which with low gain PID. And then also step response with 0.1 me. So now I'm going to pause the presentation to move us for further understanding. Thank you.
So next, because the value that we get for the closed loop system just now is still doesn't fulfill the requirement of the system. So we need to set up the proper gain by choosing a pole and two zeros for the controller. So by using this, we use the locus technique, and when we use this technique, we will get the proper gain for the that we can plug in into the controller. So after we get the proper gain, we input the gain into the controller to get the result that satisfies the requirement of the system. So the result that we get that the gain should be equal to 2. So we just multiply the KD, KP, and KI with 2, and we'll get the new value of this gain. So after that, we just repeat the same technique like Iman just said just now to get the new result that satisfy the requirement of the system. Next. So after we plot the graph, we will see that the graph that we get just now, right now will satisfy the requirement of the system as the amplitude and the time requirement for the bus to be stable is satisfied the system. Next. So this for the result of this project, you can see that the data input that we plug in for section 1 is like you just said is the mass and the spring constant and the coefficient of the damping coefficient. So for section 2, we assume the value of KD, KP, and KI, and like you can see that the below one is the final value of KD, KP, and KI. So next. So you can see that section 3 is the value of the pole and two zeros. For mention that the pole need to be equal to 0. The two zeros, the one of it must be near 0, which is 1. And another one must be a little bit higher than 0, which we choose 3. So next. So this is the output that we get. As you can see, is the result that we get from the data that we just input just now. Next. So for the, so you can see that the graph at the left side is the open loop system. As you can see that the above one is the result of the of G1, and the below one is G2. As you can see that the result for this both of this graph do not satisfy the requirement of the system. As you can see that amplitude is too high, and the time requirement for the bus to be stable is also too long. So for the right side graph at the right side, it is the locus that we use to get the proper gain for the controller. Next. So for this one, this is the graph for the closed loop system. So you can see that the 2D graph at the left side is when we use the low gain PID, but still the graph still doesn't satisfy the requirement. So we need to change it to the high gain PIDs. So after we change it, we will get the results have been satisfy the requirement of the system, which is the time requirement is, as you can see that it's only 2 seconds to for the bus to be stable. For the 3D graph for both of it is we just log the value of x2 and we'll get the 3D graph. So that's it for me. From me, thank you.
Now let's move on to the discussion. From the graph of open loop response for a unit step actuated force, it shows that the system is underdamped. Only a very small amount of oscillation can be felt by the people inside the bus. Then, based on the graph of closed loop response, the percent overshoot meet the requirement which is below the 5 millimeter mark. Although the settling time still need to be improved as it still be above 4 seconds. Lastly, some precaution steps are needed to be taken into account. One of the errors that can be avoided is by carefully follow the steps when input the data. This can purposely avoid confusion and wrong estimation when system is running. Finally, the conclusion. In conclusion, the coding that has been made helps us to reach our main objective. We can say that using this MATLAB software, it offers strong possibilities with higher interface graphics. This coding also can be applied in the industry, whether in development of mechanics or economics. Finally, this test can totally improve the knowledge while enhancing the computational skills of an engineer. That is all from our group. Thank you.